Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at transformations of functions. Specifically, we're looking at how we can transform the graphs of functions. So we're going to look at translations, reflections, and dilations. So make sure you know or have written down these rules, and just be aware sometimes they work the opposite way that we'd expect. So for example, for this one here, if you replace x with x plus h, it translates it left or right, but it goes the opposite way we'd expect. It goes left if this number is positive and right if this number is negative. And that's a bit counterintuitive because positive numbers are to the right. We'd expect positive number here moves right, but it's actually the opposite. So make sure you know each of these rules. All right, let's now look at each of these individually. We'll start with translations. So here we have the graph of fx. We're going to use this to graph f of x plus 1. So we know from our rules on the first slide that if we add a number out here, it moves the graph up and down. This one works the way you'd expect. A positive number moves it up, negative moves it down. So if I want to graph f of x plus 1, it's going to be exactly the same as this graph, except moved up 1 unit. Now, we don't want to move every single point up 1 because there's infinitely many of them. So let's just look at sort of distinctive points, like turning points. So this here, the turning point is down here. It's going to move up 1 spot. So it's going to move up to here. This turning point here will move up 1. It will be there. And same for the next one. And you can probably see now what the graph is going to look like. Other than being moved up 1 spot, these two graphs are exactly the same. So in blue is what the graph of f of x plus 1 would look like. All right, let's now take this same original graph fx. Now we're going to graph f of x minus 2. So this is going to be the same graph as the original, except we're going to move 2 spots to the right. This number inside goes the opposite way that you'd expect. So once again, rather than trying to move every single point 2 to the right, we're just going to move some distinctive points 2 to the right. So if we look at this turning point here, if we go 2 to the right, it will be over here. We're going to do the same for the next turning point and so on. Other than that, it's going to be exactly the same graph. It's going to look like this. So you can see that one graph is just a translation of the other. They're the same graph, just moved along the x-axis. All right, let's now look at reflections. So I'm going to take this graph here in blue, fx, and I'm going to graph negative f of x. So I'm sure you remember from the first slide that when we put a negative in front of the function, it reflects the graph about the x-axis. So this is like our mirror line. So reflecting this graph will be easy. Any point that's on the mirror line, in this case the x-axis, stays where it is, otherwise it just gets flipped over. So what if, instead of putting the negative in front of the function, we replace x with negative x? This one reflects it about the y-axis rather than the x-axis. So let's go ahead and do that. So any point that is already on the axis will stay where it is. Other than that, it'll be reflected. So this section of the graph here will move over here. This section of the graph will be flipped and it will come over here. And this section of the graph that just gets bigger and bigger, that will move over there. You can probably see what the whole graph is going to look like. It's going to look like that. So that's how you reflect across the y-axis. Now let's look at dilations. So dilations for me are the hardest because they depend on the scale of the graph, and sometimes if you stretch like vertically, it can also have ramifications for how it looks horizontally. So you may never have seen before the graph y equals sine x. That's okay, you don't need to know much about the graphs, but I think y equals sine x or cos x are really good for seeing dilations. So y equals sine x goes up and down, up and down, up and down forever. If I want to graph y y equals 2 sine x, it stretches it vertically. So this number 2 sort of makes it bigger vertically. So instead of oscillating between -1 and 1, it's going to oscillate between -2 and 2. So every time the graph is 0, it's going to stay 0 under this transformation. But see, when the graph hit its peak at 1, it's now going to be up here at 2. And when it hit its trough at -1, it's going to be down here at -2. So it's going to look like this. So notwithstanding my poor drawing, hopefully you can see that the blue graph is just stretched vertically to get the yellow graph. So what about y equals sine 2x? Well, this is a dilation horizontally. But this is one of those ones that works the opposite way that you might expect. So for vertical dilations, the bigger this number is, the greater this stretches. But for horizontal dilations, the bigger this number is, the more it is compressed. So because 2 is bigger than 1, our graph that we're going to draw now is going to be compressed rather than stretched from the original. So you can see that the original blue graph reaches a peak every so often. This too means it's going to reach a peak twice as often. So that's what I mean by compressed. So y equals sine 2 of x would look like this. That's what I mean by compressed. It's like you've taken the blue one, put your hands on either end, and moved your hands closer. So that's what dilations look like. Let's now look at putting it all together. So here I have a function f(x), and I'm going to use it to draw this function here. So just as there's like an order of operations, there's an order that we do things when we're transforming functions. We're going to do what's in the brackets first, then we're going to look at these coefficients, and we're going to do this last. So we need to identify the transformations that need to occur. So this 1 in here means I go 1 to the left. Remember, that goes the opposite way that you might expect. Then I'm going to focus on this number here. Well, this is a reflection, and it's a reflection about the x-axis. And after I've performed those, I'm going to concentrate on the -2, which is 2 down. So I have to perform these 3 transformations on the points that lie on this graph here. Of course, I don't want to do it with every single point. There's infinitely many of them. So let's look at some distinctive points perhaps. So let's look at this point here, which is a turning point. So what I'm going to do is I'm going to move this 1 to the left. Then I'm going to reflect it about the x-axis. So it's going to be down here. And then I'm going to go 2 down. So it's going to end up down here. So that's where this turning point goes. What about this one here, which goes through the origin? Well, I'm going to do the same. I'm going to go 1 left. I'm going to reflect about the x-axis. Because it's on the x-axis, it won't move under the reflection. And then it's going to go down here. So this point here goes down to there. And then we have a turning point here. So we're going to move it 1 to the left, then we're going to reflect it about the x-axis, so it's going to be up here, but then it's going to go down. So moving it down 2 will end up there. Now note, when you reflect about the x-axis, a maximum turning point becomes a minimum turning point will become a maximum. So the graph's going to look like this. Alright, now we're done with that. We're going to look at the opposite. We're going to use transformations to find an equation. So here I've graphed y equals x cubed in blue, and I'm going to find the graph in red. Note that I've said that there is no dilation that's occurred here, so we only need to look at reflections and translations. Dilations make finding the equation very difficult. So let's look at what's happened. We know that we have reflected the graph about the y-axis. And if we look at distinctive points like this point here, 0, 0 is actually an inflection point. It seems to have been moved 1 to the left and 2 up. So to get the equation of the graph in red, I'm going to reflect about the y-axis and also move it 1 to the left and 2 up. So to move it 1 to the left, we know that we need to replace x with x plus 1. So this would be the same graph as blue, except moved 1 to the left. In order to reflect about the y-axis, we need to put the negative in front of the function like that. And finally, if we want to move it up 2, we need to add 2. So this is the equation. If I start with this equation, I will get the red graph. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.